Okay, now we are going to see the next theorem, that is arbitrary. First of all, we have to know what do we mean by arbitrary traceable graph. If a Euler graph is said to be arbitrary traceable from a vertex V, if starting from V we can move the entire Euler line simply by moving along any edge that has not already been selected. So arbitrary traceable from V means from V I can move, I can go to the, I can create a Euler line from V. That is, from V I am starting, I can cover each of the edges exactly once, moving to each of these edges which is not selected and reaching. Right, that is what arbitrary traceable means. That is what arbitrary. For if you consider this example, here from A I cannot say it is arbitrary traceable, but C I can say it is arbitrary traceable, because from A, if you see here, if you see from A, can we draw Euler line? Think about it. From A, can we draw Euler line? I start from A, then I go to B, then I go to B to C, then C to E, E to D, right, D to C I can go, right, then 1 minute guys, here if you see A to B, now at C you have choices, like you can go to, like from A, B, C. C I can go to A itself, or I can go to E, D, right? Two paths I have. So when I get a path, like if I choose path A, B, C, A, this path, now we are stuck at A with edges C, D, C, E, D still unvisited, so you cannot reach them from A. So starting from A, one wrong choice if it is, right, if I start from A, I can go to B, C, E, I can reach here, I can cover all the edges. But the problem here is that from C there is a choice. C, if I take a wrong choice from C, I am going to A again, that means E. That means this edge C, E, E, D and C, D becomes unvisited. So that is a problem. So we cannot say that from A, sorry, we can not say that from A we can say it is an arbitrary traceable. No, we cannot say that. So for that, from where can we say this? If you consider C, from C we can say that it is arbitrary traceable. How? From VC, if I start C, any way I can go. C, E if I go, C, E, D, and from D I have only I can two ways to go. But if I take any two ways also, if I take B, A, this, if I take any two ways also, it will finally make me cover all the edges, right? So I can say from C it is arbitrary traceable, but from A, if I take a wrong choice, it doesn't cover the other edges. But in C, if I am taking, it can cover all the edges. So if I have a center position and all, then that would be of course arbitrary traceable, like C. That is like one way you can identify it is, because C is in the center, right? So it connects all the part of the graph, so we can easily say from, by looking at the graph itself, that is C is arbitrary traceable. Now we have an important theorem for us to prove, that is a graph G is considered to be arbitrary traceable from V if and only if every circuit in G contains V. So if I'm saying that there is a Euler graph G, and I'm saying that this Euler graph G is arbitrary traceable from V, only if every circuit which is present in G contains V, then only I can say that. Then only I can say that this V, from V, graph G is arbitrary traceable from V. Only if the circuits, if I'm drawing a lot of circuits for this graph G, each of these circuits contain V, then only we can say it is arbitrary traceable. We know that, but how can we prove that? So we know what is Euler graph, a graph with all vertices have even degree, so a Euler circuit would exist. Arbitrary traceable from V means you can start at any vertex V and trace any edge first and still completes a full Euler circuit. Circuit means what? It is a closed path where starting and the ending has the same vertex. So here, if I'm going to prove the if and only condition, I have to first prove the first part, that is graph G is arbitrary traceable from V. So every circuit in G contains V. This is what I have to prove. So for proving this, assume that their exit. So we have to prove that every circuit in G contains V. So let us say that this circuit, consider there exists a circuit that does not contain V. Let us consider the opposite. We are going to prove it by contradiction. So let's consider the opposite. Let's assume that the circuit does not contain V in it. Since the circuit is separate from V, that means it forms a closed loop somewhere else in the graph. Like separately it is forming a closed loop somewhere else. So now if I'm started tracing from V, you cannot reach the circuit immediately. Right. So if I now I'm starting from V, if I'm tracing, I cannot reach that circuit because this circuit is somewhere else because it doesn't contains V. So if I'm tracing from V, I cannot reach this circuit. So that means arbitrary traceable, but I have said that this graph is arbitrary traceable from me. That means if it is arbitrary traceable, you can start with any edge from V and still complete the full Euler circuit. This is impossible if this circuit is disconnected. I have to complete the full circuit if it is arbitrary traceable. But I have said that this V is not there in the circuit. This is impossible if the circuit is disconnected from V initially itself. So there is a contradiction. So we cannot say this condition. So therefore we say every circuit must include V. So that means first we consider that this G has different circuit. Let's say C1, C2, C3 and all. So if each of these circuit contain V only, then only we can say that this graph is arbitrary traceable from V. Let us say that C2 doesn't contain V. And C1 and C2 does contain V. So now this circuit C2 doesn't contain V means C2 is separate from the other parts. So it forms a closed loop somewhere else in the graph. It is not because C1 and C2 contains V, right? So if I'm started tracing from V, you cannot reach the circuit here, right? Immediately you cannot reach the circuit. But I have said that it is arbitrary traceable from V. If it is arbitrary traceable, then I should be able to go to C2. But since V is not there in the C2, how can I go to C2 then? Right. So you can start with arbitrary traceable means if I start from V, I can go to any edge and complete the whole Euler circuit. But this is impossible if the circuit is disconnected from V initially. So therefore a contradiction happen and we say that every circuit must include V in the graph. So what we are saying is that first we are going to prove that if the graph G is arbitrary traceable, then I am going to prove that the circuit would contain V. So for that I am going to consider a contradiction. By proof or by contradiction I am going to solve. First, I'm going to assume that there will be a circuit that doesn't contains V in it. Okay. So that means this circuit would form a closed loop somewhere else in the graph because it is separated from V. Now, if I'm starting from V and you cannot reach that circuit, if I'm starting from V, I cannot reach that circuit immediately. But I have said that the graph is arbitrary traceable. That means from V, you can start with any edge from V and you can still complete the whole Euler circuit. But this is impossible. This would not be happen if the circuit is disconnected initially itself. If this is disconnected, it is not possible to reach the C2. So therefore our contradiction, that our assumption is wrong, right? There's a contradiction occurs. So we can say that every circuit must include V, then only this graph can be arbitrary traceable. Then opposite side, we are saying that every circuit in the G contains V. Then I have to prove that the graph is arbitrary traceable. No matter which edge you pick from V, you won't get stuck. That is the main idea. If every circuit contains V means we start at vertex V, we choose any edges from V and continue tracing edges without repeating. Suppose you get at some vertex, that means you formed a circuit that does not include V. But this contradicts our assumption that every circuit must contain V. So here, if I'm starting at one vertex and I'm moving to each of these edges from V and I'm moving in such a way that I'm tracing any edge without repeating. But we are not going to get stuck here. But let's say if you get stuck at some vertex U which is not equal to V. Okay, I'm get stuck at some vertex, let's say U. So if I get stuck at some vertex means we have assumed that in every circuit in G it contains V. But if we get stuck, that means what? You formed a circuit that doesn't contain V. If it is a circuit, then it would contain V. Then only we can do it, right? So if you get stuck somewhere means what? You formed a circuit that doesn't include V in, but that is contradict to our assumption that every circuit must contain V. So it's a contradiction. So that means you will never get stuck before returning to V, right? So it means, so tracing is possible, so it is arbitrary traceable. Arbitrary traceable from means with every circuit would contains V in it, right? So we are going to prove it in both of the ways. In the second part, how we are proving is that every circuit in G contains V is our assumption. So how we are going to prove that? We are going to say that we are going to consider, we are going to start from the vertex and you are going to choose any edge from V. You are going to move each of the edges in such a way that you are not repeating any edges. But suppose you get stuck at some vertex, let's say U, which is not equal to V, but that means you are forming a circuit that doesn't contains V in it. That is why you get stuck, right? So but this is going to contradict our assumption that every circuit, that means this would be a contradiction because we have said that every circuit contains V in it, but if we get stuck, that means it's not including in V, so there's a contradiction. So therefore we can conclude that you will never get stuck before returning to V. So therefore it is arbitrary traceable from V. This is how we are going to prove this theorem. Okay, thank you.